accurate one, right? So we can say what? We can say that the parameters that we are choosing for any of the algorithm, any of the tasks are important, because they'll lead you to a good solution or they'll lead you to a bad solution as well. Okay. And when we talk about the optimization techniques, we are having various optimization techniques. We'll not focus on, like, we'll not go into depth about this optimization technique, but I just want to make you all clear what optimization actually is. So there are various categories of optimization technique, like constraint optimization, multimodal optimization, multi-objective optimization, combinatorial optimization, right? So, and um let us talk about the limitations of traditional optimization. We already are having, I should say that we already are having various traditional optimization approach, like we have linear optimization approach, like non-linear optimization approach, and there are various other specialized algorithms that are in the traditional optimization approach. So when we already are having something existing in the literature, then why are we talking about optimization related to genetic algorithm? When there is something already existing, why are we focusing on something else? Because there are various problems, or there are various limitations, I should say, that are with the traditional optimization problems, like linear, non-linear. These are some of the examples of traditional optimization approach. One of the limitation is these algorithms are computationally expensive, and for some of the objective functions, the traditional optimization algorithms may not work properly. In some of the cases, we also see that these traditional problem or a traditional approach do not work well with the parallel computing thing, and maybe these methods are not adaptive in nature. So because of these limitations, we are going to talk about, yeah, we are going to focus on optimization with the genetic algorithm thing. I hope this is clear. Now, because before I go into depth about the genetic algorithm, the whole idea of genetic algorithm is in evolutionary algorithm. I can say that in evolutionary algorithm, there is a subset which is a genetic algorithm. Let me talk about in brief, about the evolutionary algorithms. These algorithms have three main characteristics, right? These algorithms are having three main characteristics. The algorithms are first property or characteristics. These algorithms are population based. Okay, population based. Um, what we can understand by that? We can understand that in evolutionary algorithm, when we are trying to optimize any problem or any approach with the current solution that we are already having, right? So the solutions that we are already having, we perform some kind of computations, we perform some kind of operations on them in order to get the better solution, right? So we can say what? The current solution for a problem that we are having may be termed as population. We, in the whole discussion, will come across this term population every now and then. The second property that these category of algorithms have, they are fitness oriented, right? Fitness oriented means we are focusing on solutions. We are focusing on those individual solutions that are fit enough, right? So we'll focus on those solutions for optimizing a problem that are fit enough in the nature. So fitness oriented. The third one is your variation driven. So variation driven is what? For any of the solutions. Let me take an example. I'm doing some kind of computation and the result that I'm getting is 7. A very raw example for any mathematical computation I'm doing, and the result that I'm getting is 7. And after performing the optimization technique, or after performing the steps which are for the optimization thing, the results that the optimized result that I'm getting is 7.1, the difference of only 0.1. So the variation that I'm getting is very less. When I say I am supposed to optimize a thing, then there should be the optimization should be reflected. The optimization should be there, right? And the optimization is reflected by what? It is reflected by some kind of variations. Suppose I'm getting 7, and if I get 8.1 as a result, then I can say yes, the results have improved. So the third very property that evolutionary algorithms are having, they are variation driven. Okay, these all terms we'll see in the examples, and you will be able to be more clear about what I am saying right now. So let us go into the genetic algorithm, which is supposed to be the discussion thing of today. The history, we can say the genetic algorithm was first introduced by Professor John in Michigan University, 1965, and some article was published in 1975, and so on things. Let us not go into that. There are two main fundamental aspects with genetic algorithm. Genetic algorithm are based on two biological process. One is genetics and the other one is evolution. We come across these both are the scientists, well-known scientists to all of us. Uh, Genetic algorithm you can understand by a thing that is, as we know, genetic algorithm is biologically inspired or nature inspired aspect, nature inspired uh, orientation, right? In nature, or the environment that we are having, you might have observed one thing. You might have observed that what uh, you various species that we are seeing, including us as a human being also, slowly we have evolved and adapted with the environment. We were not the same as we are today, right? The history of human being is something else. So we have evolved and we have adapted with the nature. So we can understand one thing very clearly, that is what? To nature also in itself optimizes the species, the things that are in the nature, right? And the optimization is not all of the sudden. The optimization is not all of the sudden. Slowly the optimization process is being done, and at a stage we are saying that yes, this is the best version of the thing that we are seeing. As a human being, we can see we are the best version. We weren't the same years back ago, but nature has slowly done the optimization thing, and today we are as we see ourselves, right? So we can get the benefit from the natural system, and we can make our own system, or we can make our own algorithms, we can make our own approaches work in the same way as the nature is doing in itself, because nature is the best creator, we all know, and I hope nobody denies with this particular statement. So let us go and define the term genetic algorithm. There are various definition available in literature, and one can follow any of the definition he or she likes to say. A few of them is written over here. Genetic algorithms are type of optimization algorithm, meaning they are used to find optimal solution to a given computational problem that maximizes or minimizes a particular function. Okay, so it is a kind of optimization algorithm, optimization approach, where we are trying to get the best optimal solution. You can see one more definition. Genetic algorithm represents one branch of the field of study called evolutionary computation, in that they imitate the biological process of reproduction and natural selection to solve for the fittest solution. So in brief, we can say that these algorithms focus on optimization techniques. Um, Genetic algorithms are population-based probabilistic search and optimization techniques, which works based on the mechanism of natural genetics and natural evolution. As in the nature, we see that there are two main aspects, as we have seen over here. There are two fundamental biological processes. One is genetics, and the other one is your evolution. So this whole genetic algorithm deals with these things, right? And there are few properties that we have with genetic algorithm. These algorithms are iterative in nature. They'll repeat it again and again until we don't converge or until we don't find a optimum solution that we are finding with. And working cycles with without convergence. Without convergence is some kind of criteria, terminating criteria, where we are supposed to stop this iterative process. We are having a diagram in the near slide, and we can see the whole thing that we are stating. But one thing is there, that because the solutions are not guaranteed, not necessarily guaranteed, that I'll get an optimum solution. If I say I'll get an optimum solution which is 100% correct, this is not possible. So solutions are not guaranteed and usually terminated with local optima. Local optima and global optima are the two terms. In the next slide, I'll come to these terms in more detail. Okay, so let us talk about the very first aspect over here. You can see a diagram, and in the diagram, you are able to see various things written over here. It's a kind of flow chart. We all know what a flow chart is. And you can see that there is a start, there is a stop. Obviously, because it is a flow chart, there would be a start and a stop. Apart from start and stop, let us talk about the other things that we are having over here. The first, after start, you are able to see the next, that is generate initial population. Generate initial population is for a problem. Let us talk about this diagram in reference to a problem, right? So we are starting the process, and after starting the process, the next step is to generate the initial population, right? So in other words, what we can say here is that in the generation of population, we are talking about the possible solutions that we could have. Just a second. The possible solutions that we could have over here. So to generate initial solutions means we are generating the possible solution for that problem that we can have, right? Now, after that, what we are doing next, your arrow is coming over here, converge. After converge, if it is yes, then we can stop. Will converge is, as I said, is the terminating criteria. Will terminate our algorithm when I feel like that I have got the best solution. So if I have got the best solution, I can converge and I can stop. But if I have not got the convergence, if I have not got that terminating criteria aspect, then we go over the no part. In the no part, you are able to see two blocks. One block is your selection, and your next block is your reproduction. In selection operations, there are two main things. One is to calculate the fitness value. The second is the selection of mate. So there are two operations with selection, fitness computations, and the second one is the selection of the mate or the parent. And the next major operation over here is your reproduction. In reproduction, there are three main operators. One is crossover, mutation, and inversion. Once we are done with this crossover, mutation, and inversion, this arrow is again going to this what? Checking of the convergence criteria. See, after doing all of this, we'll get some kind of result. We'll get some different results, and we can check over here whether the results that we are getting is good enough. Can we converge or not? If yes, we can stop. If no, we can repeat this process again. So you are able to see what? You are able to see that this process is repeating. It is going in a cycle that it was written over there. So in this way, the cycle is repeating itself until we do not have a criteria which says that you should terminate. See, when we say iterative, uh, for example, let us take a program, for loop example. I hope everybody understands what is a for loop. And for a for loop, we write a condition that this particular loop should terminate after 5 iterations. So we can have the convergence criteria either after a limited amount of step. We'll say that this particular algorithm will repeat itself 5 times, and whatever results I will get, I'll consider that result as an optimum result. The second thing is what? The second thing is we will repeat it again and again unless we do not get the best optimal solution. So in this way, we can understand what? From this slide, we are supposed to take what? We are supposed to learn the selection operations. We are supposed to learn the reproduction operations. And in that, we are supposed to learn these 3: crossover, mutation, inversion. And in the selection, we are supposed to talk about how are we going to compute the fitness, how are we going to select the mate, and all those things. So selection, when we say, or we can say that the genetic algorithm is having 3 building blocks. 3 building blocks are what? The first step, that is this one, population creation. I should write one over here. The second building block is your selection aspect. The third building block is your reproduction thing. So these are the 3 building blocks on which the genetic algorithm stands. Okay. Now let us take our discussion into more depth. Let us dive the details. So when we talk about, from here, we'll talk about the operators, the genetic algorithm operators. The main operators are encoding, the first one. Encoding is what? For a solution, for any of the solutions that we are having, how are we going to encode them? How are we going to represent them? What I can say, how are we going to represent that solution? So encoding deals with the representation of the solution in genetic algorithm. And representation is because, see, we may have different types of solutions. We may have real value as a solutions. We may have binary values as in solutions, and different other things also as in solutions. So we are supposed to encode them. And once we encode something, we are supposed to decode it as well. So that is encoding. Talking about the representation, the first operator of genetic algorithm. The second one is your convergence. We are talking about this term since last 5 minutes. So convergence is your criteria which decides the termination. When to stop this whole process, when to stop this iterative process. So that will be decided by the convergence criteria. Next is your mating pool. Mating pool is from the population. We are selecting some of the solutions. See, from a given solution, from a given population is your solution. From a given solution, we are selecting few of the solutions and keeping them in the mating pool. And we are selecting those solutions which we find are fittest. So mating pool is a place where we can say we are going to generate the next solutions, or we are going to work on the optimization thing. The next operator is your fitness evaluation. How to evaluate a solution. We said or we are saying that the whole genetic algorithm or the evolutionary algorithm deals with the second parameter, that is fitness. So we are doing some kind of fitness check on the solutions that we are having, and we are rejecting the solutions that are not fit enough. We are selecting only those solutions that are fit enough to be proceeded forward. The next very operator is your crossover operator. So crossover is a technique. We are having various examples related to this, and I'll talk about it in detail in the further slides. So we can just understand from here is what crossover is, some kind of technique by which we are trying to, we are trying to uh, have changes, or we are trying to modify the solutions for, we are modifying the solutions. Next is your mutation. Mutation is again a reproductive technique. I said these three are the reproductive technique: this crossover, mutation, and inversion. So mutation is also one type of operation done. We'll discuss about it with an example so that you get a more clear aspect about what a mutation is. But for now, I can just say mutation is a step, is a process. Suppose I can just give you a normal example. Um, we suppose we have a, let us talk about any of the pet animal that we are having. Suppose we are having a cat, and cat is having a specific property in itself. Cat is supposed to be a cat, and it has some specific property. And after some time, or if some of its properties changes, we by any of the means, it has changed its property, and the shape that a cat is having has changed. So it shows what, that some kind of mutation, some kind of changes has been done into it, and the solutions that we are getting is mutated solutions. You'll get a better view with the examples in the further slides. Inversion is also one of the operator with reproduction only. Inversion, you can understand what, to move from one optimum solution to the other one. For all of this, I have specific examples, and from there you would be able to get the picture more better clear. Okay. There are different genetic algorithm strategies. The main one is simple genetic algorithm, steady state genetic algorithm, messy genetic algorithm. So these are some of the strategies, and these strategies are a bit different from each other. Let us talk about this simple genetic algorithm, steady state genetic algorithm, and messy genetic algorithm. Okay, I'll just give you a brief over here. Simple genetic algorithm is what? In simple genetic algorithm, the first step is to start, and after starting, we are doing what we are. The next step is to generate the solutions, the random solution that we can have by have for a problem. And the next step, once we are decided the population, we will evaluate every solutions that we are having. Okay. So once we are done with that, we are evaluating what? We are evaluating every possible solutions. And when we evaluate every possible solutions, we will get a fitness score, right? After the fitness score, what we do, once we have calculated the fitness score, now we should check for what? We should check whether the convergence criteria is met or not. If the convergence criteria is met, we can stop the process. And if the convergence criteria is not satisfied, let me go to this particular diagram, and I'll just brief little bit about here. In this diagram itself, we can see the process of that simple genetic algorithm strategy. See, if the convergence criteria is not met, right? If the convergence, we have talked about starting has been done, initial population has been generated, and after that we calculate the fitness score of all the solutions, and we check for the convergence criteria. If converging is there, we can stop. If convergence is not there, then what we are supposed to do? Then we are supposed to select, we are supposed to select NP. Suppose what I say, suppose I am having 100 solutions over here, 100 possible solutions I have computed. Now what we are supposed to do, I am supposed to select some percentage of solution for this selection and reproduction criteria, for reproduction aspect. Suppose that percentage or p value I have kept it as 20. So from this 100 solutions, I will select 20 best solution. Okay, 20 solutions I would select based on that, this calculate the fitness value. After calculating the fitness value as values, I'll get the fitness of all the solutions, and I'll select the 20 best solutions and proceed further. So simple genetic algorithm is saying what? When we are doing the repetition, when we are doing the selection and reproduction task, I am not supposed to do it on every solution. Instead, I will select some percentage of solution. That can be 20%, that can be 30%, 50%, 40%, or any of the percentage which is being decided. Right? So on that limited number of solutions, I would perform that selection and reproduction task in order to get the best solution. So this is your simple genetic algorithm. In the same way, we are having steady state and messy genetic algorithm. Right now, we are not focusing on these, but just keep in mind the strategy of the simple genetic algorithm, and we can proceed further with this. And one more thing is there. Okay, let me go on the next slide, and then okay, the important genetic algorithm operations that we are going to discuss. First one is your encoding. As I have already said, fitness evaluation and selection, mating pool, crossover, mutation, invergence, and convergence test. Okay. So the first operator that we will discuss now is your encoding. When we say the very first operation, which is encoding. Okay. So encoding for any of the encoding schemes for genetic algorithm, two things are involved. We can say what a term population is being repeatedly used. I'm saying population and individual. Okay, two terms I'm taking again and again. Let me once again clarify that so that it does not have any doubts in your mind. When I say population, population are group of solutions, right? Populations are group of solutions, and individual is what? Individual is a single solution. As we know, we are individual. I'm individual person, and with everybody I can say we are a population. In the same way, individual term, whenever I'll be using, I'm talking about a single solution. And when I say population, population means we are talking about a group, we are talking about sets of individual. Keep this in mind, and then we can talk about this. When we encoding on a major words, we can say that we are having four different types of encoding: binary, real, order, and pre-encoding. We are very well aware with the binary term. Binary encoding means we uh, the gene or the chromosome are being represented with the help of zeros and ones. The second one is your real value encoding. In real value encoding, we represent the gene in the terms of value or the symbols. The third one is your order encoding. Order encoding is a representation of sequence of elements, and there are specific problems where we cannot work with binary or the real value encoding. We are supposed to have a different encoding schemes. For example, this order encoding, we are aware with the problem of traveling salesman problem. Okay, traveling salesman problem is a sequence. The result that we obtain is a sequence in which the salesman travels to every city, and he is not supposed to repeat a city even once. Only the starting and the end point can be same, and other cities are not to be repeated. So there are various problems in literature in which the ordering is important, and where such kind of things are there, we go with the order encoding. The other name of order encoding is your permutation encoding also. And there is one more encoding, that is tree encoding. Tree represented in the form of tree. So let us talk about this in detail. Okay, I have already talked about this, that genetic algorithm uses two distinct elements. One is your individual. Individual is your single solution. Population is a set of individuals. Okay, before I go into the details of that encoding scheme, there are two terms, two very important terms to genetic algorithm. One is phenotype and genotype. Okay, so phenotype and genotype is what we can understand it like. See, if we talk about nature, if we talk about ourselves, we know that uh, there are various genes in ourselves as a human being. And what a chromosome is, chromosome is collection of gene. Okay, chromosome is collection of gene. And what we can say, and any of the basic structures of these chromosomes may be called as a genotype, may be called as a genotype. Let me take an example so that you might be able to understand it properly. Suppose I am having a problem and there is some kind of objective function given to me. Let it be any of the problem, right? And there are various different variables that are being provided to me in that objective function. Let that variable be a1. The second variable that is given to me is a2, a3, and so on up to a of n. So this a1, a2, a3 are what in this objective function? What are these? We are having a1, a2, a3 up to an. And these are the design parameters. These are the parameters on which this objective function is to be built. Okay, so a1 is your first parameter, a2 is your second parameter, a3 might be a3 is your third parameter, and so on. So we can say what? We can say that what we can say, we can say that these parameters may have different values. A1 can have a different value at a specific instance of time. Suppose at this instance of time, the value of A1 is 0.5. The value of A2 is suppose 1. The value of A3 is suppose 3, and so on. So at a particular instance of time, these parameters would have a value. So at any instance, the value that these parameters are having is known as a genotype. is known as genotype. So in totality, what we can say, in totality, we can say that genotype and phenotype, and one more thing, the mapping of genotype to phenotype is important. We can say for every parameter that we are having, there is a phenotype. And if there is a proper mapping between genotype and phenotype, then we would be able to get a better efficient solution. We'll be able to get good solutions. So the term genotype and phenotype for any individual representation. This phenotype and one more thing, phenotype and genotype, we are talking in terms of a individual representation. In the previous slide we are having two types of representation: individual, the second one is your population. So for individual representation, phenotype and genotype. So let us talk about the first encoding scheme technique. The first encoding technique is your binary encoding. In binary encoding, we know that every chromosome would be a combination of zeros and ones. You are able to see over here. There are zeros and ones written over here. And in this particular example, obviously the length is fixed for A and B, both chromosomes. There are two chromosomes, chromosome 1 and chromosome 2. For both of them, the size is fixed, but obviously we can also have variable length of chromosome. So we have represented it as a zeros and one. You can understand one more thing. We are having an example to this. The example is your knapsack problem. Knapsack problem, I'll just brief it out for anybody who is not aware with what it is. Knapsack is what we can say, it is a bucket or anything in which we can keep things. This is a story about a thief which he is going to some place for stealing things, and he has a knapsack which is of fixed size. And as a thief, he will try to keep in that knapsack those things from that house or that place which are having which would take him to a greater benefit, because the size of the knapsack is limited. He can keep only a limited number of things in that knapsack. Then obviously he'll try to steal those things from that particular house which are costly, right? So that is the problem of knapsack. Okay. Now suppose, let us take an example over here itself. In an house, suppose there are various things. Let us count how many chromosomes are here. 1 2 3 4 5 6 18. 18. Okay. Let us take an example. There is a house and there are 18 different things in that particular house. For that 18 different things, suppose the thief has not chosen the first thing. The thief has not chosen the first element in that particular house. So we have represented it as a 0. The thief has stolen or taken that second element from that particular house. So we have marked it as 1. He has also taken that third element and kept in the knapsack. So we have marked it, the third element or third place, as 1. Similarly, the whole you can see zeros and ones. So 0 is for not taking that particular element, 1 is representing for taking that particular element and keeping in the knapsack. Obviously, because we are talking about specifically about the knapsack problem, we need to keep in mind the storage space. Suppose I say that the storage space of this particular knapsack is only 10. only 10 elements could be there. So the 10 elements 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So these are obviously 10 elements. So these are the 10 elements that that particular thief has stolen from a house. And while deciding which element to take and which element to reject, he has kept in mind one thing, that he should take a element which will ultimately provide him the more benefit, or whenever he sells that particular thing, he may get the maximum benefit out of it. So this is your binary encoding way of doing the things. Now from here, uh, just a second. Okay. From your this thing, one more aspect uh, we should understand is that encoding encoding is important, because the way you represent your data will ultimately take you to a better solution. If and once we are doing encoding, we'll definitely do decoding also. So encoding and decoding strategies or techniques are important. And for specific type of data, we can use only specific type of encoding processes. Not every encoding scheme could be applied to every problem. Okay. So the advantage that we have from binary encoding is that with binary representation, a faster implementation of genetic algorithm operators could be done. But the drawback that this encoding scheme holds is that we need to convert the data into binary form. So the conversion part would definitely take time, and the correctness would depend on how accurately you have represented or you have done that binary conversion. So this is the drawback to binary encoding. But definitely with all the encoding techniques that we'll discuss, the binary encoding one is the most simplest one. Let us talk about the second one, that is real value encoding. Real value encoding is used, uh, we can say what we can use the real value encoding for optimization problem which are continuous in search space, and direct representation is done. So we are not required to convert that particular value into binary again. But definitely we can see an example. There is a chromosome A which is having value 2.345. We are having a chromosome B which is having value 7.65 something. So these are real numbers, and we have used the real value encoding over here. But you can also observe a thing over here. That is what, can't we convert this into binary? Can't we convert this 2.345 into binary numbers? Definitely we can convert it. Definitely we can convert it. We are having um, methods by which we can convert this real value into binary also. But an important thing, if we are thinking about converting a real value into binary and encoding thing, we are supposed to know what? We are supposed to know that in order to in order to keep this 2.345, how many number of bits I would required? How many number of bits I would require to keep this value? That is important. So for finding that also, to decide how many number of bits I would require to store this 2.345 and 7.6543, there are mechanism by which we can find out that. And ultimately, if we find out how many numbers of bits are required, we can store this real value encoding also in binary form. The examples where this real value encoding is used, we can use this encoding. Yeah, these encoding schemes are used to find the weights of neural networks. Definitely for neural networks, we can go with where we are finding the weights, we can go with this real value encoding thing. The third encoding that we are supposed to discuss is your order, or the other name to this encoding is your permutation encoding. As I have already said that for every problem, we would not be able to represent.
Ma'am,
Yes,
sorry to interrupt, sorry to
yes,
disturb you. I have one question
yes,
regarding before slide.
yes, ma'am.
Hello, am I audible?
Yes, ma'am, you are audible.
Yes, this is the problem is neural network find weights of for inputs of neurons to train the network for wanted output. Real values in chromosomes represent corresponding weights for inputs. That means that weight is represented like something is 0.34
Yes,
or 2 point something or 7.8 point something, whatever it
yes,
is. Then
yes.
how we can do that binary conversion or
Ma'am, yes, I got your question. See, as I said that we are having mechanism by which the ultimate thing is what? If I need to convert this particular value in binary one, I should know the bit number of bits required, right? So for calculating that, we are having formulas. Like I can just state it for you that I can calculate the number of bits. Let us take that number of bit as n. So n is equal to log 2 in bracket xu minus xl upon epsilon. This is a formula. You can find this. You can search on Google itself. By computing this one, we can get the number of bits that would be required to save. And the important aspect is your epsilon value, because we are dividing it by. Let me just write it over here, and you can find that. Find it. See, it is. I'm not remembering the exact one, but it is something like that. Log 2 xu, sorry, it's distorted, xl upon epsilon. Okay, so the epsilon value is important. If we are having a good epsilon value, then the accuracy that we would get would be the best one. But you can definitely go with the, I think this is the correct one, formula, but for details you can search on Google. There are various formulas by which we can decide the number of bits, and once I know this number of the bits required, then I can convert this particular into binary and store it. I hope, ma'am, I have answered your question.
yes, yes, thank you.
Okay, so the order permutation, order encoding one, see, let us directly talk about the example with this traveling salesman problem. There is a salesman uh, who is supposed, I guess we are having a yes, I'm having a diagram also. See, you can see a graph over here, and there are A, B, C, D, and E nodes. Let us suppose these nodes are the cities, and there is a salesman. He's supposed to visit all these cities. There is a salesman, let us name it as S. So he's supposed to visit all these cities, okay? And he is not supposed to repeat any of the cities while traveling. While traveling, is not supposed to repeat any of the cities. Only the starting point and the end could be same. Suppose he's starting from A, so he can come back to A again, but he cannot repeatedly go on B, neither on C, nor on E, nor on D. So that is your traveling salesman problem. So TSP problem is having like in itself, there is a matrix over here, but this is the initial matrix, and you are able to see infinity. Infinity is this is the first matrix. Instead, I should say that this is the first matrix to this solution. And this infinity is just stating what, that we are not having a direct path between A to C, and we can see also from A there is no connectivity which is going directly to the C city. So let us focus on the encoding part. So the result that we will be getting for this problem would be a sequence. Let me write a random sequence. I'm not writing the exact sequence for it, but just a random sequence. The salesman started from A, then he went to somewhere B, then C, then D, E, and again A. I hope maybe this is a wrong answer, but I'm just writing a sequence in order to get a picture more clearer. So you can see that in the only the start and the stop point is repeated in this particular sequence. None of other values are being repeated. So there are specific problems in which the sequence is very, very important, because if the sequence is not proper, that would not be justifying the answer. That would not be justifying the answer. So for those problems where the sequence are important, we go with the order encoding thing. Now, let us go to the fourth encoding for this discussion. The fourth encoding is your tree encoding. Tree encoding is again a very nice encoding scheme. And also in tree encoding scheme, we are able to see what? You are able to see a tree, binary tree over here. And okay, from this particular tree, or from this particular binary tree, I should say instead, you are able to see A, then B and D. And again, the second sub branch that you are able to see is your C, E, G, and F. So tree encoding, we can understand it as for some specific problems that exist where the representation, the objective function that we are having is stating to have a tree like architecture. Suppose for a tree, for any of the process, if only I am traversing at B and D, then this is not required. C, E, G, and F is not required for me. So we can go with tree encoding thing, and you are also able to see that, and there is a term in order, pre-order, and post-order. These are traversal schemes: in order, pre-order, and post-order. And in order, in the in order thing, we know the left, right, and left data and right is being traversed. In pre-order, we know that the data is to be traversed first, then the left child, and then the right child. And for the post-order, we are able to, for the post-order, we know we have to traverse first the left child, right child, and then the data part. So there are various problems for which we can have, or for which we can have only the tree representation. So for such problems, we go with the tree encoding one. So this is all about the encoding thing. Once we are done with the encoding thing, once I have use the best encoding scheme that I can use or I can go with, the next step, I should say, is to evaluate the fitness. So the second operator that we will discuss is the fitness evaluation and selection. So fitness evaluation and selection is one of the important step before going to the conversion. Best solution or the fittest solution. Objective is to choose the individual which are the best one. So if I do not get the best solution, then what? if I do not get the best solution, we get the next population, and for the next population we have to create the mating pool and repeat this process. So ultimately the selection is to be done. Ultimately, see, there are two things. One is fitness evaluation and selection is written over here. Keep this in mind. These are two things. One is to fitness evaluate and the second one is selection. So selection is what? Selection is the process of creating the population for next generation. And while selection, we keep in mind the fittest solutions, fittest individual in that particular population. So in totality, both of them are fitness evaluation and selection. These are techniques for selection. The first thing is the technique for selection, and these are important strategies with like these are important topic to the discussion. There are various other selection strategies also, but I have written some of the mostly used selection strategies. To start with, the first one is your canonical, Rowlett wheel, rank based selection, tournament selection, steady state selection, and there are various other, as I already said. Anybody interested in this particular thing could search in the literature and go on with it. Let us discuss about the very first one, that is canonical. So in canonical selection, what actually is happening, what we are doing. See, uh, here in this particular method, it fitness of every individual fitness of every individual is calculated. See, you can see fitness is defined as ith individual as well. Fitness of I is equal to fi. Fitness of I is equal to fi upon f. So using this particular thing, we are calculating the fitness score for every individual solutions that we have. Okay, and once we are done with that, this f bar is the average evaluation of all the individuals in the population size of n. Let us consider one more thing. The size of the population is n. Keep this n in mind. The total size of the population is being represented by capital N. So we can calculate this f bar is equal to summation of I is equal to 1 upon n fi upon n. So we get what? We get fitness of I, and we can also compute the f bar using this particular uh, formula. We can say it as. And we calculate once we have done this particular step and this particular thing, then what we are supposed to do? We are supposed to calculate what? We are supposed at See, uh, if I know the fitness value of each individual, if I know the fitness value of each individual in the population, then I can do what? I can do the summation of the fitness value and divide it by the total number of size of the population that we have done over here. By this, we are doing this itself, and it is represented by f bar. Now, at any instance of current population, any instance of current population, uh, in canonical selection, the probability that an individual in the current population is copied and placed in the mating pool is proportional to their fitness. This is the main thing for canonical one. That is, it is saying what? And let us uh, talk about this also. Here, the size of mating pool is p percentage into n for some p. Convergence rate depend on the p value. So only the individuals with the highest fitness value would be selected and proceeded further to the mating pool. See, and how many number of individuals actually we are going to select? would be this P percentage. Would be this P percentage. Suppose I am having, let us take an example to make it more clear. Suppose I am having 10 solutions. For all the 10 solutions, I have evaluated the fitness score, right? And suppose I say the individuals that I would select or the P percentage value that I will keep is 20%. So from these 10 solution, 20 percentage is 2. Okay, the 20 percentage of 10 is 2. So I will select the top 2 scorer, top 2 best solutions with the highest fitness value. Only that much. If I say the fitness value, if I say the P percentage is 40%, if I say the P percentage is 40%, then I would select the top four solutions, yeah, top four solutions with the highest fitness value. So ultimately, canonical selection method is focusing on the highest fitness scorer solutions. And the punchline that we can say is how much to select. How much to select, that is important. Why not I select the whole 100%? Why only 10%? Why only 20%? And why only 50%? So this percentage is important. And how we can have a question, how to decide this percentage? How many individuals should I select? So at the time, these uh, when anybody is programming with this particular things, he or she should decide this percentage P. So we can say the programmer or the designer to the problem could decide this P value, P percentage value, because the value is important and it will ultimately take you to either good or bad solution. If I say I'll select 80%, so if you're selecting 80 percentage from this 10, that means 8 individuals you are selecting, then the results that you would get may not be optimal, because you have ultimately selected everyone for the next generation process. So if you have selected everybody from that solution, so the optimality or the results that we would get may not vary. So that is the canonical selection method, one of the simplest selection method we can say. Then next, very used selection procedure is your Rowlett wheel selection one. This is used like broadly, this is used many a times. So in this problem, let us first see, we are able to see a diagram over here. This is a wheel. There is a wheel. A Rowlett wheel is actually a game thing, and you are able to see various things written over here. This is a wheel. This wheel could be rotated clockwise or anti-clockwise. Second thing, you are able to observe a point, that is selection point. So when I rotate this wheel, something would be pointing over here, selection. For this particular instance of time, you are able to see this. There is a 3 marked over here, and this selection is pointing to this 3. Achha, let me tell one more thing. You can visualize it as there are 5 solutions. 1 solution, 2, 3, 4, and 5. We are having 5 solutions. And for these 5 solutions, we have given some proportion on this particular wheel. How this proportion is being decided, I'll talk in the next slide. For timing, let us assume the proportion of individual solution 1 is 31. For solution 2 is 5%, for solution 3 is 38%, and so on for 4 and 5. So according to the percentage they are holding, that much space they have occupied on this particular wheel. And we are going to rotate this wheel either in clockwise or in anti-clockwise direction. And after rotating, definitely it would stop somewhere. So wherever this particular wheel is, wherever this selection point is pointing, that particular individual would be selected. Keep in mind that we are talking about the selection criteria. We are supposed to select In canonical method, the selection was based on the percentage. We are saying we'll select 10 percentage of individuals. So 10 highest fitted solution we have selected. But here we are not doing that thing. Here we are doing what? We are selecting the individual based on the selection point. So for instance, 3 is being pointed. So for the mating pool, I'll select this solution 3. I'll repeat this wheel again. Maybe it can point to 31. Sorry, this 1. So the next solution I can select is 1. The main, or what we can say, the thing to ponder over here is what? Obviously, see the chances of individual solution 4, 5, and 2 to be selected is reduced. Why it is reduced? Because they are occupying a very less space on this particular wheel. I'm not saying they wouldn't be selected. They can be selected. Obviously, they can be also be selected as a solution to be taken forward for the mating pool. But the chances of their selection has reduced because they have occupied a very limited space on this particular wheel. See, the two only have a 5% of space in this particular wheel. Individual 4 is having only 12% of area occupied on this particular wheel. Individual 5 is only having 14%. So the chance of their selection is being reduced over here. And by reduction, the profit that we are getting, we can see one thing, what this 38%, 5%, 31, what are these? These are fitness score. As I have discussed in the previous canonical method also, that for every solution, by some means we will calculate the fitness value of them. By some means, I'm stating it again, that by some means we will calculate the fitness value. And once we get the fitness value, we are deciding whom to take to the next process, or whom to take to the next step. So in this method, by this method, we are selecting what we can, we are selecting those, or we are trying to select those particular solutions which like who are more fit. Let us take an example. I hope this wheel section is clear, and by an example this would be more clear to every one of us. And you can see one more thing that has been written is P of I is equal to Fi, summation of I is equal to 1 to n f of I. See how much percentage I said now. I have already said that these are occupying some. 4 is having 12%, 5 is having 14%, 3 is having 38%. How this percentage has been calculated? We can decide it by this. See, a particular sub area representing genetic algorithm solution is selected to be winner probabilistically, and probability that the ith area will be declared as this particular. So in other words, we can say that individual having higher fitness value, the chances of them to be selected becomes higher. Let us take an example from here. In this example, you are able to see 5 individuals. These are 5 individuals, 1, 2, 3, 4, and 5. For this 5 individual, this is their chromosome representation. This is a chromosome representation. Okay. And after that, you can also you can also understand, or you can also check this, the binary of this. This is the binary, 107 is written over here, and the binary of 107 is this chromosome representation that we have written in binary. 984 could be represented by this, 261 is represented by this binary one, 928 is this, and 907 is this one. Once we have done this, we are calculating this x, fitness f of x, and percentage of total. Okay, so we have calculate and see one, the main thing that is written over here, f of x Example, population of 5 for f of x is equal to minus 1 by 4 x square plus 2x plus 5. This is the function that is given to us. Using this particular function, using this particular thing, we have calculated this value. You can calculate it later on. Placing the values over here, and we are able to get this particular 6.82, 1.11, 8.48, and so on. And for the total percentage, for total, and see, you can also see from this fitness score, observe one more thing. You can observe that the individual 3, this one, the individual 3 is the fittest because it is having a score of 8.48. The next fittest solution is 1. It is having a value of 6.82. Okay, so these are the two best solutions. And the weakest solution that we can also observe over here is this 1.1. So this 1.11 is the weakest one. Now, after doing this, we have to calculate the percentage of total. So you can get, after calculation, you can also observe that 6.82, the total in 100%, it is 31. For 1.11, the percentage value that we'll get is 5%, and so on, 38%, 12%, and 12 and 14%. See that this 31, 5, 38, 12, and 14, that only is been written over here. You can see for the individual 3, 38%. How did we get this 38%? I said I'll talk about this in the next slide. So the 38% is being calculated from this particular table. And whatever percentage that we are getting, accordingly, we are drawing this Rowlett wheel. We are dividing the space, we are giving the space to the individuals on this particular wheel. Fine. See, after this, the next question that should come in mind is, how many times are we going to repeat this? Like this Rowlett wheel is going to be spun how many times? So the number of times the Rowlett wheel is spun is equal to the size of population. Here, see, in this particular example, the size of the population is 5. Okay, so 5 times we'll repeat that wheel, and we will select whatever resultant we are getting. Whatever resultant we are getting. So the size of the population is the number of times the Rowlett wheel will be rotated. And with the hope that doing all this, by following all these strategies, we are actually trying to have we are actually trying to give lower probability to those individuals which are having fitness score lesser to be selected. Okay, so this is your Rowlett wheel example. There is a drawback also. That drawback is what? This leads to a lesser diversity and hence fewer scope towards exploring the alternative solution, because we are reducing the chance of those individuals which are having less fitness score to be selected. So we can say that this can take us to a lesser diverse solutions, or it may also take us to premature convergence problem. So this is a drawback. Then also I can say that this is one of the mostly used selection strategy. The third important selection strategy is your rank-based selection strategy. In rank-based selection strategy, what you can say it as enhancement of your Rowlett wheel. We said there is a problem. See, we are talking about this particular problem in Rowlett wheel. That is, we may have a less diverse solutions. We may lead to a premature conversion. Premature conversion is terminating before or converging with a local optimal solution, something like that. So to reduce, or in order to fight with this drawback, this rank-based selection strategy is there. There are two simple steps to rank-based selection method. The first is what? All the individuals are arranged in ascending order of their fitness, right? You can understand it as We have individuals. We have calculated their fitness score. Okay. Let me go on this example only and I'll explain you the rank based method also. See, so it would be easier. Rank based selection strategy is saying this. It is saying for all of the solutions, we are having 1, 2, 3, 4, 5. These are the 5 individual solutions. For all of them, we are calculating the fitness. So I have calculated this fitness by some means. We are not saying this 6.8 to 1.1. These are the fitness score. Once I get the fitness score, I will rank these individuals. I will rank this individual. And how will I do the ranking? The individual with the lowest fitness score would be ranked 1. So we can see over here that 1.11 is the lowest score. That means the rank to individual 2 would be given as 1. Sorry. The next one is here 2.57. So individual 4 would be given rank 2. Then fifth one would be given rank 3. First one would be given rank 4, and the 8.41 would be given the rank 5. So in ascending order from the lowest fitness value, we are going to provide rank 1, 2, 3 and 4. I hope this is clear. See, and once the rank is, your first step is that much. What I have discussed is all about your step number 1. Once ranking is done from lower to highest, the second task is each individual, then we can follow any of the canonical or Rowlett method. Once ranking is done, you can follow either Rowlett wheel method for further evaluation, or you may follow the canonical method also for further evaluation. Okay, so let us go to the example and see. This is a good example we are having. Let us take 4 individuals with fitness score. There are 4 individuals, 1, 2, 3 and 4. Okay? So 4 individuals we are having, and we have calculated the fitness score also. This is your fitness score 0.4, 0.05, 0.03 and 0.02. And according to the fitness score, the rank is given. See, this is the lowest value 0.01. So the rank given to this 4th individual is 1. Then 0.03 is the next, rank 2, rank 3 and rank 4. Okay, so these are the ranks given over here. Now this RW is your Rowlett wheel, right? And RS is your rank based. Two important things. Let me rub this and this also. Rowlett wheel. According to Rowlett wheel, what would the Rowlett wheel would have done over here? Rowlett wheel would have done what? It might have given this 0, because 0.4 is the 0.4 is 80%. So according to Rowlett wheel, which is given by RW, the area occupied by this individual one would be 80%. Now see, you are able to see two things. One is a blue color marking and the next one is your gray color marking, right? So the gray color marking is for your Rowlett. So you are able to see this 80% space given, this one from here to here. 80% space would have been given to the individual one, 10% to individual two, and so on so on. But according to your rank based selection strategies, we will give what? We'll do this. The percentage, see this particular point. This is an important thing over here. The percentage area to be occupied by an particular individual I, according to rank based selection, is this. Ri by summation of I is equal to 1 by n Ri. This is somewhat same. See, this formula is same. This is same that we used in that Rowlett wheel one. Only that we have replaced some. There was Fi. We have replaced it by Ri, and nothing difference is over here. So according to this, we are getting 40%, 30%, 10%, 20%, and this. For individual for 10%. You can observe one thing. Now the probability, here also the probability of individual one still to be selected is more because it is having 40 percentage. But at the same time, the probability of the individuals with less score, the chances of them also to be selected has increased somehow, has somewhat increased. So now, prior you can see what the individual 4 was having only 4%. Think of a scenario on this a wheel occupying only 4% of space. How much chance that particular individual is having to be getted selected? It will have a very low chance. By rank based, we have increased what? We have increased the probability of all the individuals being selected to some extent. And we can obviously say that this is an improvement to this Rowlett wheel selection strategy. Okay, so this was your rank based method. The next method that we are having is your tournament selection strategy. In tournament selection strategy, this is a different strategy, like somewhat different from the previously discussed one. Let us see the example and then we can see. See, um, let us see this example. This one, just a second. Let us see this example, and it would be more clear. See, we are having individuals 1, 2, 3 up to 8. We are having 8 individuals, and accordingly, the fitness score is being calculated. The fitness score for 1 is 1.0, for 2 is 2.1, 3.1, 4.0, 4.6, and so on. For every individual, we have selected what we have selected the we have calculated the fitness score. And according to the tournament selection strategy, what we are supposed to do? We are supposed to select the individuals. We are supposed to select individuals to in or obviously tournament means what? Tournament in games, while playing games we use the term tournament, and we start with everybody and later on the filtration is been done, and lastly finally we get one single solution, the best, the team that is winning. The same has been done over here. In trial one, yeah, in the phase one, or in the first iteration or something, any word you can use over here. In trial one, suppose you have selected individual 2 and individual 4. So individual 2 is this one and individual 4 is, and after that, from both of them, the individual having the highest score of fitness would be selected. So we can see from 2 and 4, 4 is having a fitness score of 4.1, so obviously 4 is selected. In the same way for everybody, next trial we have done from 3 8, in between 3 and 8, and from 3 and 8 we can see that 8 is having a fitness score, so accordingly these are being selected. This is tournament selection strategy. But see, observe, if in the selected one, you can observe a few things. You can observe few things. One is that what? You might see the repetition of the same individual. As for individual 4, you can see 4 is over here also and 4 is repeated over here also. For individual 8, you can see individual 8 and individual 8 again being selected. So we can observe that there might be chances of the same individual to be selected more than once, right? So and one more thing can happen. One more thing can happen is, suppose there are 2 individuals. Like for our case, we are not having that particular thing, but we can have a scenario that the 2 individuals that we have selected for the trial, both are having the same fitness score. There is a tie between both of them. Then what we can do? For our example right now, we are not having any of the solutions. But for example, suppose 2 and 4, both are having fitness score 2.1. Then in that condition, if there is a tie, then we can use some other mechanism. We can use some tossing mechanism, and we can break this tie. Tossing mechanism, toss head and tails like thing. Tossing is that. So we can use some tossing strategy mechanism and break this tie. Whomsoever would be selected by this by the tossing mechanism would be selected and proceeded for further steps. Okay, so this is your tournament selection example. This technique is computationally more faster than both roulette wheel and rank-based selection strategy. The next and the last to be discussed for this selection strategy is your steady state selection strategy. Okay, so what is steady state uh, selection strategy, or it is one of the simple strategy, but every time this steady algorithm may not work or may not take us to the best solution. See, like the tournament selection, it also selects the parameter called NU. So you are able to see this word NU. Same as we did in tournament selection, there is a parameter which is named as NU. So NU is what? NU is the number that can be selected. NU is a number that can be selected from that population. So NU individuals with highest fitness score would be selected. See, again I can say that same example. Suppose I'm having this 10 solutions and the value of NU is 20% or 2. So from this 10, I would select only 2 individuals, and that 2 individuals would be what? That 2 individuals would be those which are having the highest fitness value. So steady state selection method is simple. It says according to the NU value decided by the programmer, it will select that NU individuals which are having the highest fitness score from the population. And one more thing, huh, the difference that is over here from the previous things discussed is what? We will replace, what we'll do, I said from the 10 solution, I'll select 2 solutions. And that 2 solutions would be replacing the 2 worst it would be replacing the 2 worst individuals from the population. Let me take this, and here I'll give you an example because it is already written over here, and from this we can be more clear. See, we are having 8, only focus on this much part. For steady state selection mechanism, only focus on this one, individual and fitness score. It is saying what? Decide a NU value. Suppose I say the value of NU is 2. मैंने कहा we are having 2 as a value of NU. So that 2 best scorer are which one? One is 5. It is having a fitness score of 4.6, and the next best solution that I'm having is having a value of 4.1. Now this 2, this 4.6 and 4.5, this will be replacing whom? These 2 will be replacing the 2 worst solution in this particular individual one. So 2 worst solution in our problem, this would be going, and this 7 will replace them. So steady state selection mechanism is taking few individuals with the highest fitness score and are being replaced by the worst population that they are having. So this was the steady state selection algorithm. You can do the comparison of these selection strategies over here. Let us not read all these things. And all the selection strategies are being like compared in reference to population diversity and selection pressure. So this is the thing, you can read it. Let us go to the next topic. Now till here, we are done with the 3 steps: encoding, fitness evaluation, select. And once you have selected, all this things, or this all these 4 to 5 strategies that we have discussed were in the reference of selection. So once we have selected the best solutions by any of the mechanism, we'll take that solutions and keep them in the mating pool, right? So we have discussed till here. Now the next very important strategy is your crossover, mutation, and inversion. See, these three, crossover, mutation, and inversion, are reproductive steps. I have already said that the genetic algorithms are having 3 building blocks. One is your population, second is your selection that we have done from year and year, and the third one is your reproduction. And also keep in mind the reproduction uh, operators. Let it be crossover. Obviously crossover, let me talk about more about crossover. Crossover is one of the operation in this whole strategy which is taking more computation time. Crossover is occupying one of the more one of the time taking step. One of the most time taking step is your crossover. Let us talk something about crossover also. See, reproduction, crossover, mutation, and these are the 3 main operations. One is crossover, mutation, and inversion. Okay. Mating pool. It was I have already talked about this, that once we have selected the individuals, uh, we keep those best individuals in the mating pool. Okay. But few things to keep in mind about the mating pool is what? A mating pair. See, we have taken solutions, we have selected solutions, and we have kept it in the mating pool. Let this be solution A, B, C, D, E, F, something like that. Suppose I'm having 6 solutions, 6 individual solutions. So in the mating pool, I'm supposed to make mating pairs. I'm supposed to select at least 2 pair. See, so a mating pair, each pair consists of 2 strings are selected at random. Now here, these are the best solutions that we have taken. After that, we can select 2 random solutions. See, so I can select FE. I can even select B and D together. So there is no like uh, we are having specific methods also in order to select from the best one also. But for timing, let us assume that randomly we are selecting the individuals in the mating. Okay. So this is to be kept in mind about mating pool. And once these pair are been selected, listen to it properly, that once this mating pair are been selected, then we go for the crossover. Or we can say once the mating pool individuals or pair from mating pool are been selected, we go for the reproductive steps, or we go for the very first step, that is crossover. So let us go to that crossover discussion. Again, one more thing. As we talked about encoding, we talked about binary, real value, order encoding, and pre-encoding. So whatever encoding strategies you have used prior in the first step, that same would be like, we need to perform the operation accordingly. If I've used binary encoding, I should use the crossover techniques that fits fine with crossover one. If I have encoded using real value, then I should go with the crossover mechanism that deals with real coded one. This is important. The type of encoding that you are doing at the time of crossover, you will also deal with that same time of crossover mechanisms. So, okay. Let us first talk about, see, I will talk about these. Let us first talk about the binary coded one. I have done my binary encoding thing, and now the crossover techniques. So there are various, see, I have written few of the names. In literature, you may find various other mechanisms and techniques also. These are few of them. One is your single point, 2-point uniform crossover, half uniform crossover, 3-parent crossover. In the same way, we also have various other crossover mechanism also. So let us discuss about them. These are very interesting and easy to understand. Let us first talk about the single point crossover. In single point crossover, see, we have chromosome 1, chromosome 2. Means these are two different solutions. These were the best solutions. And randomly we have chosen these two from the mating pool. Single point crossover states what? From this in this chromosome, we'll select a point, K point, right? We'll select a K point. You can also see we select a K point lying between 1 and L. Let it be K. So suppose I have selected this as the point. Here also I marked it as same. And then we can cross over. We have done the crossover where we have crossed this and we have crossed this with this. And we have obtained two different solutions. We have obtained two different individuals offsprings. So you can see what the offspring 1 that has been generating is holding this part from chromosome 1 and this part from chromosome 2, and ultimately they are the new offspring. In the same way, but single point crossover will make a single cutting point, will make a single cut on that chromosome. So this is your single point crossover. Then in the same way we are having, let us focus on the example and you'll be able to understand it in a clearer way. So 2-point crossover, obviously as the name is stating, the same thing that we did in single crossover, here we are supposed to do it with 2 points. So in that chromosome 1 and 2, I have made two cuts. One is here, purple color, and this one is here. And after doing that, what we have done in 2-point crossover, you are able to see what that this portion and this portion is the same for offspring 1. Okay, this part, and the swapping that we have done is between the middle portion, this and this. So this is your offspring 1, this is your offspring 2. So 2-point crossover will have two cuts, and the middle portion is swapped in the left, and also one in this particular example, the swapping is been done only in the middle portion, rest remains the same. In the same way, if you're not swapping the middle portion, we can swap the left right portion as well. So that is your 2-point crossover. In the same way, you are having the next strategy, which is uniform crossover strategy. Okay, so uniform crossover strategy, you can observe from the diagram. Okay, see, parent 1, parent 2. Okay, uniform crossover, parent 1 is given, parent 2 is given. You can observe a different thing. Also, we have got offspring 1 and offspring B. But a different thing or extraordinary thing that has been lying over here is your status. A word named as status, and something over there is also been written. This status is what you can see in status. There are zeros and ones only in the status. Observe, you are having the combination of zeros and one. These zeros and ones are what? These zeros and ones are toss. I hope you understand tossing. Heads and tail we are using sometimes for taking the decision, and some in genetic algorithm also we have few of the tossing mechanisms, and by using that tossing mechanism we are performing this uniform crossover mechanism. You can see that we have done the tossing for the first bit. For the first bit we are doing the tossing, and the result that we have obtained is 0. So you see this one. If a coin toss is 0, do not swap. If coin toss is 0, do not swap. So you can observe that just a second. You can observe that the first tossed value is 0. That means it is saying do not swap it. That means in the offspring A and in the offspring B, just copy the value. Just copy the value of parent A and parent B directly to offspring A and B. So we have done that same thing. 1, and 0 are being directly copied at offspring 1 and 0. For the next value, we have done the tossing and we have got the result as 0. Again, we have copied from parent 1 and parent 2 directly. So we have copied this. Up to here, we have copied same. The next toss value we are doing here is 1. So if coin toss is 1, swap. So here, because we are having 1, we are going to swap. Swap means from parent 1, we'll keep it, the gene from the parent A would be copied to the offspring B, and the gene from parent B would be copied to the offspring A. In the same way, every time we are, for every bit, we are doing the tossing process, and accordingly we are performed. If 0 we are getting as a toss, we'll swap it. We will not swap it, and if we are getting 1, we can swap it. And this could be vice versa also. One can choose to have, if coin toss is 1, we'll swap. One can choose to have, if coin toss is 0, will not swap. So it depends on the programmer. So this is your uniform crossover. Synonym, like as we discussed about uniform crossover, in the same way, the next enhanced crossover technique is your uniform crossover with the mask. See, only difference that we are having in uniform crossover with mask and this particular technique, which is simply uniform crossover, and this is your uniform crossover with mask. The difference is what? The difference is this mask. Again, you may say that, ma'am, that mask is also the combination of zeros and ones also, and in the previous diagram also we had that same thing, zeros and 1. But see, in uniform crossover, every time we are doing tossing for every pair of bit. Mask is, obviously it is a combination of 0 and 1, but mask is what? Mask is a random bit pattern. This particular zeros and ones that we have got over here, we have not done any kind of tossing. We have just taken a random zeros and ones combination and named it as mask and kept it over here. By this, the benefit that we are getting is what? See, every time if we are doing tossing that we did in this uniform crossover one, it is time taking. It will consume your resources. In this particular status, I said we are doing tossing for every bit. So it will take your time, it will take your energy, it will take the resources of the computation process. And mask is what? Mask is a random bit pattern with zeros and ones. And also we can say that instead of this particular mask, we can use the parent one more parent chromosome, and you can use it as the mask. Let us not add that thing into this. Let us keep it simple. Let us keep this as simple and do it as what? Mask is a random bit pattern of zeros and ones, and we can decide if the mask value is 0, what to do. So in this particular example, we have taken if mask, in mask, if there is 1, then gene is copied from first parent. So, and if it is 0, copied from second parent. So the mask value is 0. It is saying what? If it is 0, copy the gene value of second parent. So we have copied from second parent, and this is 4. If the mask value is 1, this is 1, copy it from the first parent. So we have copied from first parent and kept 2 over here. Again from parent 1, so 2 is been copied, and this in same way this whole is been done. So this is your uniform crossover with mask, and because of usage of mask, we are able to save the resources consumed by your program. Okay, then next, in the same way, moving forward, we are having half uniform crossover. In half uniform crossover, actually it is based on your Hamming distance concept. You can see there are parent 1 and parent 2, and the Hamming distance is 4. You can observe from this pair, you are having 4 as an Hamming distance. And once we calculate the Hamming distance, we can do, if we can again do the tossing part. So if toss is 1, then swap the bit, else remains the same. See, you can observe that we are doing tossing not for everyone. We are doing tossing not for everyone. We are doing tossing only at 4 places. So this remains the same. So you can see nothing has been changed over here. Here we have done the tossing and we are saying what? If the toss value is 1, we will swap. So definitely we have swapped this. You can observe this is same, this one and this one is same. For the 4th place, you can observe the value is 0. 0 is stating what? Do not swap. So this is same. For 1, we are swapping. So we have swapped this and so on. So this is your uniform crossover. Okay. Prashant sir.
Yes, ma'am.
Prashant sir.
Yes, ma'am.
So
Yes.
are we done with the time? Because it is
Uh,
11:41. So shall I summarize it, because we are having many more things, but due to the time constraint, we would not be able to like come across all those things. Can
no
I
problem.
summarize all?
Sure. Yeah, you can summarize that. Yes. Thank you.
I'll summarize it to um, the challenges and the future work. See, we didn't talk about. I hope you have got the point about the crossover. After crossover, we can perform mutation. See, mutation is what? As I said, we can perform a mutation strategy if required. Suppose while doing this experiment, while doing all these things, the solutions that I'm getting is not optimum enough, not good enough. In that condition, what I'm supposed to do? I should take a decision before convergence that shall I mutate something? Shall I change something over here so that may I can get a good solution? So before the whole process stop, if you are observing that you are not getting a solution that was required, that you are expecting, you can do the mutation process. And maybe after doing that, you may reach to some good solutions also. You may reach to some of the good solutions. So there is where the mutation comes in the picture. And inversion. Inversion is what? I'll just define it for all of you. Inversions, as we understand as a computer person, is if we are having 1, the inversion of 1 is 0. The inversion of 0 is 1. So if you want a very minimal change in your chromosome pattern, if you just want to change a single bit, you can only summarize it as like if you want a very minimal changes in the chromosome pattern or in the solutions that we are working with, we can go with the inversion part. So there is where the mutation and inversions come into the picture. But let me go to the last slide. Just a second. I'll go to this. There were many other things to be discussed. Anyhow, mm, challenges and future scopes in the genetic algorithm. One of the challenge with genetic algorithm aspects, it is the computational cost it incurs in itself is very high. And also, as I started with this word parameter configuration itself, we started our whole discussion from this particular issue itself. So how to decide the proper parameters, because if the parameters chosen are not good enough, it will not take you to the best optimal solution. So there are various other challenges also, but to keep it simple, I've just taken 2 points. That is, one is your computational cost and the parameter configuration. And for future scope, see, I'm again stating it as there are other future scopes also, but we have just stated few of them. So future scope is what? There are areas where people are working is there should be an appropriate way to choose the degree of crossover. How much to do? Like we have discussed about crossover. So what would be the degree of crossover? Why should be it single crossover? Why should be it double? Or why should be it any other crossover technique? So the degree uh, to choose the crossover or mutation operation is like important. And we should also talk about the convergence. Premature convergence problem is what? Suppose we are not getting the conversion is to terminate, and if your problem terminates prematurely before it is expected to, or if it is not giving you a good solution and taking you to a local optimum solution, so this is also again a problem. How should I avoid my algorithm not to like prematurely converge? And the last one is an open problem, that scope of simulating the natural evaluation process should, such as the response of human immune system and the mutation in the virus. Like right now we are dealing with this corona virus, so genetic algorithm is a field where people are definitely they are working, and many other works are still there that we can go on with. So this was all about the session. Thank you. If anybody is having any question, I would be happy to answer it. Let me see the check. Okay, Biswajit Senapati sir, thank you. Like at in one of the slide, spelling is correct. I'll definitely correct it. Thank you very much. Because we have not talked about inversion, sir. Can you explain about inversion to move from one optimum? Definitely, we did not. We due to the time constraint, I would not. I was not able to like reach over there. So
Also, since we are done with the time, so the questions which has not been answered, or we can take those questions and you can share those questions on the WhatsApp group which is there as well, or you can
yes,
mail
sir.
ma'am on her official email ID, and if you have any queries further, you can ask her directly. I think that should be okay, right, ma'am?
Yes, sir.
Yes. So thank you very much, ma'am, for very informative understanding and a description of genetic algorithms. And I know you would have continued further, but because of time constraint, we couldn't do that. But that's anyway, I think, a lot of information for the students to actually ponder upon. And if there are references, you can actually look up to. And if there are any queries further, if you want to have any clarification personally, you can mail ma'am on her email ID. So thank you, ma'am, once again for this wonderful session which you had on genetic algorithms. And I would invite our head of the department, Professor Subhash Chandra sir, to come up and convey the vote of thanks. Thank you, ma'am. Thank you very much, sir.
Thank you, Prashant. Thank you. Really, Sindhuji, it was indeed a very nice session you have handled. Particularly, you have covered a brief about genetic algorithms, and it's even the future is scope about the genetic algorithms. Even genetic algorithm in such a detail, how the biological system inspire in the development of genetic algorithms. You have covered also that with the proper examples of taking traveling salesman problem. It was very nice indeed. And how the genetic algorithms are being used for optimization of a solution from given set of solution. You have also covered and explained very beautifully that. And we express very sincere thanks to you for a very nice and
Sir, thank you.
interactive session. Most welcome. I think the students, the delegates, the participants, they have really enriched their knowledge, and they have enjoyed the about this algorithm development is one of the part of machine learning and all the things. Thank you, ma'am.
Thank you, sir.
Over to you, Prashant, for the next session. Whether there is a break of 15 minutes or...
Right, sir. There is a break for 10 to 15 minutes, and then we'll continue with the next session.
Okay, then I think to keep the recording of the lecture, you should log off, then once again log on. So we'll have the clipping automatically of all the sessions. separately.
Right. Sure, sir.
Okay. Otherwise, later on you have to cut the slides.
Right, right.
And this will easy to upload the sessions on the Atal portal as well. And I am seeing the WhatsApp messages. Many of the participants are asking for
Okay.
sir attendance sheet, feedback sheet. I have mentioned in WhatsApp. Please don't worry about that. You are on Google Meet. Each and every login and session is being recorded automatically. You not to be worry about that. Only
Right.
focus toward the gaining the knowledge, because good experts are there in this platform. Thank you all the participants and delegates. Thank you, Sindhuji. Over to you, Prashant.
Thank you, sir. Thank you very much. Thank you, ma'am, once again. Right. The delegates are requested to be online. No need to log off if you don't have any bandwidth problem. So be with us, and I'll just turn off my video and turn off the recording, but you can be with us online for 10 minutes and we'll start the session soon, right? So thank you very much, delegates, for patiently, listening to the lectures, and hope you have enjoyed it. And the next session is on regression analysis, linear and nonlinear regression. The session is with Professor Dilip Kumar Yadav, Professor and Head Department Computer Applications, NIT Jamshedpur. So just in a short while, we'll be back. I request all of you to be online, right? Thank you very much, and I will see you soon. Thank you.